When
Sir, do
material
we have
feed
to
rate,
write this note?
any confusion?
Sir,
Can I
do we have
continue?
to? Sir, do we have to write this notes, or you will send on the group?
Notes I will send to you today. I think
Okay.
until capillary rise, I gave you notes, right? Check your
Yes,
previous
sir.
note which I have sent to you.
Yes, sir. Yes, sir.
Until capillary rise 2h by r cos theta, that I gave the notes.
Yes.
Isn't it? Last formula in that page. Now, this is a new topic. Today, I will send to you, hold this chapter. Okay? Now, I told you, let us finish now. If you read, you will understand. It's not a difficult thing if you read, but most of the time you're lazy. That's what you want me to be with you, writing notes, making you understand. That I will do. But first, let us finish it. Read the notes, make how much possible you can understand, and independently you do it. After that, during holiday, I'll give you extra 45 minutes daily, one hour period enough. Then everything I'll give in detail. Then you can check your note, you can correct whatever it is. But keep the notes printed with you. Computer, you cannot make corrections there. It's difficult. Because that's a photograph, right? Okay, thermal expansion. So here you can see during summer, this wires sagging like this. That means expanding. During winter, this becomes tight. So when you fix these electrical wires or telephone wires and all, you must know how much expansion taking place during from winter to summer. Or railway tracks. You can see between railway tracks, there are small gaps placed. Especially in Saudi Arabia and all, overall railway from here to Riyadh, we are putting a railway line. In that cases, temperature goes in Riyadh and all sometimes 5 degrees. It goes to 55 degrees. So that much temperature variation, this rail will expand. So that expansion, if there is no gap, this rail will bend. So some gap should be provided for this expansion contraction. Then buildings while constructing, we can see small gap between two blocks, they will give providing it. Then only expansion, during expansion, it will not break. So this is what mainly we are going to study. When we focus on expansion length, that's called linear expansion. When focusing on expansion of area, that's called aerial expansion. When focusing on volume expansion, volume change, that's called volume expansion. Now we have to study this relation. This is a very important topic. A very easy topic also. Listen. First one, linear expansion. Let us take a material of initial length LO. For example, 1 meter. On heating, this is expanding. 1 millimeter here, 1 millimeter here. So delta L become 2 millimeter, or let it be 1 millimeter overall. This is 0.5, this is 0.5, 1 millimeter is delta L. Now I am taking a 2 meter wire, initially 2 meter wire. Then I am heating with the same rise in temperature, same. So here, how many length it will expand? 1 millimeter wire expanded 1 millimeter. And if I'm taking 2 meter wire, how much a time it will expand? 2 millimeter, right?
Yes.
3 meter wire, if I'm taking, it will expand 3 millimeter. Agree? That means 1 meter expands 1 millimeter. Like that, each length increasing, that much expansion will be there. So in general, we can say this change in length of the wire is directly proportional to original length. Original length is larger, expansion is larger. Shorter the wire, lesser the expansion. Then if you keep on heating the same wire, length will keep on increasing. So we can say delta L is proportional to L naught delta T. Okay. This is a starting now. Okay. In this wire, we have taken LO. On heating, its length increase. That length is LT. Change in length produced is delta L. So we can say this delta L is directly proportional to original length and rise in temperature. then delta L is equal to, there must be a proportionality constant. That's again alpha. So this alpha and proportionality may bit confuse you, but don't confuse here. For the time being, you take it like that. This is alpha. Okay. Then L naught delta T. This alpha is known as coefficient of linear expansion. Linear means length. Then alpha is equal to delta L by L naught delta T. Unit, this is meter by meter, this is temperature Kelvin, this will cancel. Then alpha is equal to delta L by L naught delta T, Kelvin to the power minus 1. These alpha values are given in your textbook. Okay, I will just read out some values. In textbook, oh, I don't have second text. In part 2, roughly I'll tell you. Alpha, if you are taking textbook, it's written linear expansion, like a table, it's written. In that, they have written alpha of aluminum. Okay, like, for example, 2.01. And here on the top, they have written into 10 to the power minus 7 meter. That is constant for all values. So you have to consider 2.01 into 10 to the power 7 meter. What does it mean, this alpha? Look here. If L naught is equal to 1 meter, delta T is 1 Kelvin, then alpha is equal to delta L Kelvin to the power minus 1. That means you take 1 meter of aluminum, heat through 1 degree Celsius, you can see expansion is 2.01 into 10 to the power minus 7 meter, very small expansion. That's the meaning of alpha. So alpha can be defined as the change in length of a material of unit length when it is heating through unit rise in temperature. Did you understand?
Yes, sir.
Yes, sir.
Yes,
sir. So this is the idea of alpha. Okay, coefficient of linear expansion. These values are usually given in your textbook, and numericals also it will be given. Now, here we can write delta L is equal to alpha L naught delta T. Delta L is nothing but LT minus LO, isn't it? Because initially it was LO, now it is changed to LT after heating. The change in length is delta. So we can say LT minus LO, alpha LO delta T. Or LT is equal to change LO this side, LO plus alpha LO delta T. LT is equal to L naught into 1 plus alpha delta. This is the formula of linear expansion. Now, when we talk about aerial expansion, you see, it's very easy. You imagine an area, a thin sheet like this. Okay, like this, a thin sheet, imagine, metal sheet. Initial area, A naught. When you're heating, change in area become AT. Substitute here. See what I'm going to do? Look here, just I'm going to change it. Delta A is proportional to initial area delta T. Delta A is equal to, instead of alpha, I'm writing beta. Beta is known as coefficient of aerial expansion. This is A naught delta T. Now this is beta. Delta A by A naught delta T. Meter squared, meter squared. It will cancel, Kelvin to the power minus 1. Beta is equal to delta A naught delta T. If A naught is 1 meter square, delta T 1 Kelvin, beta is equal to delta A. So coefficient of aerial expansion or superficial expansion can be defined as change in area of a material of unit area through unit rise in temperature. Then here again, delta A is equal delta A is equal to beta A naught delta T. Here AT minus A naught is equal to beta A naught delta T. AT is equal to A naught into alpha A naught delta T. AT is equal to A naught into 1 plus beta delta. See? These are the answers. Is it clear? Now volume, if it comes, same idea. This will be delta V is proportional to V naught delta T. And beta become gamma. Everywhere the changes will come. Finally here, Vt is equal to V naught into 1 plus gamma delta. Gamma is coefficient of cubical expansion. These are the three derivations. There, I will give the note. You can go through it. Is it clear? Did you understand?
Yes, sir.
Now,
Yes.
next one, relation between alpha and beta. Relation between alpha and beta means suppose this is L0. This is also L0. After heating, this become after heating, each side increase to LT. L0, L0. This become LT. This also become LT. So totally, this is L0 squared. That is the area of this. Here it become LT. AT is equal to LT squared K. Now we need relation between alpha and beta. So here we can write in relation. Now delta A. Delta A is equal to AT minus A0. And delta A is equal to AT means LT squared minus L0 squared. Okay, this is delta A. Now we know, before that, let us write beta. We know beta is equal to delta A divided by A0 delta T. That means beta is equal to delta A is what? AT minus A0. AT minus A0, right? Divided by, this is A0 delta. Now, beta is equal to, what is AT? AT can be written as LT squared, right? LT squared. That can be written as LT squared, L0 squared divided by L0 squared delta. Now here, we can just substitute. Beta is equal to, what is LT? L0 into 1 plus alpha delta T whole square, isn't it? Beta is LT square. L0, this is L0 square divided by L0 squared delta T. Now beta is equal to, this L0 squared you can take commonly out, will cancel out with it. Then 1 plus alpha delta T whole squared minus 1 by delta T. This will cancel out. Okay, this L0 will come out. Then beta is equal to 1 plus, we have to open this bracket. So A squared plus B squared plus 2AB. So 1 squared plus, okay, 2 into 1 into alpha delta T plus alpha squared delta T squared minus 1 divided by delta T. So this one will cancel. Alpha squared is very, very small value. I told you 10 to the power minus 5. Squared is very small value. So we are neglecting that value. So remaining now beta is equal to 2 alpha delta T by delta T. Delta T cancel. Beta is equal to 2 alpha. Clear? If coefficient of linear expansion is alpha, coefficient of aerial expansion will be beta. Agreed? Same way we can show gamma also. You can see derivation is there. You can read it. Clearly we can see gamma is equal to 3 alpha. Okay. So beta is equal to beta is equal to 2 alpha. Or alpha is equal to beta by 2. Gamma is equal to 3 alpha. Then alpha is equal to gamma by 3. Okay.
Guys,
What is that?
It's a very special video because I am having a very short interview between
now
Hacker
equate
and me. And of course,
gamma by 3 is equal to beta by 2.
Gamma
Gamma is equal to 3 by 2 beta. What is the disturbance?
Sir, Rahis is talking.
Sir, Zaid.
If you're not interested, just quit the class. No problem.
Sir, they are just lying,
Don't
sir.
disturb.
I didn't do any disturbance.
Sir, it's Rahis, sir. It's his voice.
Whoever it is, I'm telling you, just leave the class. Otherwise, I will stop it and I will cancel that portion. I'll go to. And if you're continuingly this way, I will just declare it closed. That's all. Because if you're not non-corporate can do no other way. I told now. Unusual expansion of water. Unusual expansion of water. Unusual expansion of water. Look here. Water has a specific property. That means if you plot a graph, and even you can write a lecture note. You don't have to just sit idle. Take a blank sheet, A4 size sheet, and write faster. Then you will get, I mean, what I'm writing here, almost all I'm writing. Only thing that introduction part, you have to copy from your photocopy, the photo image. Otherwise, you can note down, right? Lecture notes. If you want, you can cooperate. And if you don't want to study how much I do effort, you will not do. Look here. So this is here volume. Okay. Here temperature. Suppose you are taking water and measure the volume. When water we are cooling, usually its volume decreases like every material. But when it reaches 4 degrees, every material will go still cooling until 0 and all. But water below 4 degrees, instead of cooling, it expands. That property you will study in physics. This expansion property of liquid is known as water below 4 degrees is known as unusual expansion. Unusual, not usual expansion or anomalous expansion. Anyway, we can call it. And the graph come like this.
So this only happens in water.
Which one?
This only, sir, that it contracts when there is less temperature.
Below 4 degrees. Below 4
only
degrees,
in water
or
in other materials as well.
See, you can check it. You take a bottle full of water, okay, and keep in freezer. You can see after solidifying, bottle will break. Even in cold countries and all, water pipes also break sometimes because water expands more than the volume when it was a liquid. So every material, when solid comes, it will be smaller. Solid volume is less than liquid state for every material. But ice is not like that. When it is below 4 degrees, it starts expanding. 0 degree, its maximum expansion will come. Clear? Right. So this is the graph.
Yes,
see, at 4 degrees Celsius, volume will come to minimum. And again, more than 4 degrees, it will expand. So minimum volume comes at 4 degrees. So maximum density of the water also 4 degrees. Above 4 degrees, volume increases. Below 4 degrees also volume increases. Okay. Now, this is very useful for aquatic animals living in polar regions. The reason, suppose this is a lake, okay, and there is fishing inside it. Suppose during winter, temperature goes down. So suppose if this is 16 degrees Celsius, water will also come to 16 degrees. It continues 15, 10, 9, like that. When it becomes 4 degrees Celsius, water is also 4 degrees. Everywhere is 4 degrees. But now when the outside temperature is 3 degrees Celsius, first upper layer becomes 3 degrees Celsius. But upper 3 degrees Celsius is having more volume. That means less density. If you can draw, volume increases, density decreases, because mass by volume is equal to density. Sorry, density is equal to mass by volume. Volume decreases, density increases. So below 4 degrees, if you are cooling, that water will expand. So volume increasing, density decreases. So 3 degree water is lighter than 4 degree water. So what happened? That 3 degree water will float above this. So this is 3 degree, just below 4 degree will come. Again, heat goes. Now this become 2 degree. This has become 3 degree. This become 4 degree. That means 2 degrees less, still less volume. So density is still lighter. So 2 degree will be above, 3 degree below, 4 degree last. After that, it becomes 1 degree. 1 degree means again, see, volume decreasing, density, volume increasing, density decreasing. So first it will become, again here, this is 1 degree, then this is 2 degree, this is 3 degree, this is 4 degree. Then it becomes 0 degree atmosphere. Then that becomes ice, see 0 degree. Maximum volume, minimum density will come there. Then we can see first one will be 0 degree, then 1 degree, then 2 degree, last will be 4 degree. That means here this forms ice. Once it forms ice, ice is a good insulator. It won't allow heat exchange from inside to outside. That's why here you can see if you break this ice, you can see water inside. Their aquatic animals are safe. If water is contracting like other materials, then zero. Ice will be high denser like a solid. Every material solid is density, more density. So ice will come down and 4-degree water will be on the top. That keep losing heat. Finally, entire water become ice. So all these animals will die. So this unusual expansion, it's again, it stresses the existence of God. So this is clearly says how the earth protect the aquatic animals. So this is also known as gift of unusual expansion is assumed as gift to the nature of gift to the aquatic animals living in polar region. Otherwise, they would have died completely.
But sir, we are destroying it because of global warming.
But that is global warming.
No sir, like we are. No sir, like we are destroying it by global warming.
That's what I'm telling you. It's but now, if the people are not alert, within 50, 60 years, what many places will be underwater. Jiddan will go underwater because it is almost sea level only, this region and all. Next heading, bimetallic strip. Bimetallic strip. Look here. Bimetallic strip means you can see there are two metal strips kept like this. One metal like this, other metal like this. Two metal strips. These two metal strips are made of different materials. Since this is, say, for example, aluminum, say this is copper. This has 1.01 into 10 to the power minus 5. Okay, meter, this one, Kelvin to the power minus 1. This has coefficient of linear expansion, 5.01 into 10 to the power minus 5. That means copper has more expansion. If you're heating it, both will expand. But aluminum will expand less, copper will expand more. That means this will go to a circular shape now because they cannot expand together. So copper will pull, copper has more expansion, right? So aluminum less, so it will go upward. This material will turn upward like this. It will be like this. Now you see, this is copper. It has more expansion. Aluminum has less expansion. It will bend like this. If you're cooling, copper will cool more. So that should have less expansion. It will go like this. This is copper. This is aluminum. So this can use as a switch in the refrigerator, automatic switching system and all. This bimetallic strip uses a switch. I will tell you how is it. Look here. Suppose this is a refrigerator. Okay. Here, there is a bimetallic strip and a cooling system is there. A cooling system is there inside. Bimetallic strip is like this. Okay. Here it is kept this way, bimetallic strip. Two materials. Okay. Now it is not connecting here. This is connected to compressor. This compressor only deciding cooling. If current flows here only, compressor will work, inside cooling will come. Now we are setting this for, say for example, below 3 degrees Celsius, you don't want to cool it. So you adjust that knob. So bimetallic strip is adjusted, the distance actually. Then what happened here? When you open the refrigerator, hot air goes inside. So when it is heated, now bimetallic strip will go like this. See, it will bend like this. Now circuit will work, it will cool. Compressor will work. Once it's cool, this will go exactly opposite side. Isn't it? This bimetallic strip will go exactly opposite side. So it has no connection. Again, when it is hot, suppose you're opening the refrigerator and closing it. Now hot air went inside. Now you can see with a shake, it again starting. That means again bimetallic strip started turning this side. Compressor on, it working. So this is a system of bimetallic strip. Clear? As switches, they are using it. Many places they are using it, this one. Okay. Next heading. Specific heat capacity. Specific heat capacity. This is CV, specific heat capacity. Okay. Look here. or you can take it S, not CV, S, specific capacity S. Specific capacity means it is the amount of heat required by unit mass of a substance to have a unit rise in temperature. This is all you studied in 9th also, I think, isn't it? Specific capacity. Suppose you are taking a material, 1 kilogram. Heat, keep a thermometer. Supply an amount of heat. If it is temperature rising, say for example 21 to 22 or 34 to 35, if there is a unit rise in temperature, the amount of heat supplied is called specific capacity. For water, specific capacity is 4,200 kilogram per joule. The joule per kilogram. Joule per kilogram. That means 1 kilogram water, if you are heating through 1 degree Celsius, there you have supplied 4,200 joules of heat. This is the meaning of heat capacity. Okay. So formula, if you are writing, look, S is equal to specific capacity, amount of heat divided by mass, delta T. Amount of heat required per unit mass for unit rise in temperature. This is joule, kilogram, Kelvin, or joule, kilogram to the power minus 1, Kelvin to the power minus 1. This is specific capacity. Now, if you are multiplying by SM here, SM is equal to Q delta T. This is joule per Kelvin. Kilogram is not there. This is known as just heat capacity. Heat capacity. Okay, S into M into S. This is called heat capacity. So heat, if you want Q, you can write M as delta T. Mass into specific capacity into delta T. So these are the main formulas you should know in this topic. Clear? Now, change of states of matter. Change of state. This change of state they are showing in ice. 3 types of change of state: solid to liquid, liquid to gas, and solid to gas. That's called sublimation. So for that, there is a graph. See, this is a graph for it. First, what they are doing here, this is ice at minus 10 degrees Celsius, ice. When you're supplying the heat, temperature of the ice will increase. Ice will reach 0 degrees Celsius now. 0 degrees Celsius. Now, the amount of heat supplied is mass of the ice, specific heat capacity of the ice into rise in temperature. Rise in temperature is 10. After reaching melting point, we can see temperature will not change. Usually what's happening, the temperature you are giving, increasing the kinetic energy of the molecules. But when change of state comes, kinetic energy will not change. Instead, molecule gets separated. It's a change of state. They are realigning. So molecules go far apart. For that, they need energy. You know, molecules in solids are very close to each other. So to get separated, they have to do work. That work they are taking from heat. And with more heat energy, they will change the state. So this time, there is no change in temperature. Remember that. This time, there is no change in temperature, but change of state taking place. For 1 kilogram of ice to completely water at 0 degrees Celsius is 3.35 into 10 to the power 5 joule per kilogram. This is known as latent heat of fusion of ice or latent heat of melting of ice. Clear? So here we can say Q2 is equal to, this is for 1 kilogram. If M kilogram means M into LF. Now that solid completely melted. Again, what we are doing, rise in temperature comes. After that, see, so throughout this region Q2, there won't be any rise in temperature. At the same time, we can see at the beginning, only solid. When we come here, liquid part will developing. So in this region at 0 degree, solid and liquids are coexisting. Two states are coexisting simultaneously. And both will have 0 degree. Water is having 0 degree, that solid also having 0 degree. Because pure melting ice. Once it's completely molten, at this end, the right end, only liquid. Now again, if we heat, we can see temperature will rise. Now again, kinetic energy is increasing. After reaching 100 degrees Celsius, after reaching 100 degree here, after reaching 100 degrees Celsius, again stop increasing the kinetic energy, but here again change of state comes. See, again change of state. This time, this is Q3. Q3 is equal to mass into specific capacity of water, this region water, into rise in temperature. Here it is 100. If any other material, that change of state you have to write there. At this point, Q4 is equal to mass into latent heat of vaporization. Latent heat of vaporization required around 2.26 into 10 to the power 6 joule per kilogram. See, very, very bigger than this. Clear? So that much heat we have to supply. Now from here, again, here gas and liquid, vapor and liquid coexisting. Then from here, you see, again, there is a rise in temperature that will go superheated steam. So here, this is Q5 is equal to mass into specific capacity of steam into rise in temperature. So maybe here in this graph, 110, but you can heat up to how much you want. So total energy required for change of state from -10 to 110 is Q1 plus, Q2 plus, Q3 plus, Q4 plus, Q5. This question can be asked for smaller regions. How much heat energy required for water at 0 degree, ice at 0 degree to reach water at 100 degree? So see, ice at 0 degree. This is become water. See, water at 0 degree. So you have to add Q2 and Q3 only. If they're asking from -10 ice to 100 degree boiling water, then Q1, Q2, Q3. Like this, we can treat this graph. Any doubt?
No, sir.
So here, 2-3 things here based on this I can tell you. The temperature at which that these two existing, what melting water and solid, liquid and solid coexisting. That's called melting point. This melting point, every metal has different melting point. But at normal pressure, it has a normal melting point. Similarly, it has a normal boiling point. I will tell you how this melting point and boiling point change. Okay, look here. A body is boiling. First, let us see melting. Look here. Here, suppose there is an object. Molecules are packed. It's a solid. Okay. If I am compressing it, these molecules will come closer. Isn't it? When it's coming closer, that become. Wait. Before that, I'm telling you, this is the solid. Molecules are arranged this way. If I'm heating it, these molecules will move apart. Then this become liquid. So that volume increasing now. Molecules are now far apart. Volume increasing. In the case of ice, what's happening? Reverse happening. Solid will be like this. When it is melting, molecules of water come closer. So here while heating, molecules come closer. Now, without heating, I am going to change the state. Just exert high pressure on all the sides. Then these molecules will come closer. That will become like this. This will turn to water. This phenomenon is actually known as regulation. Regulation. That means if you exert pressure on the ice, then that will have a change of state. Once pressure is removed, that will come back to solid. This can be easily explained. You take a support here, wooden support, and here there is ice kept here, ice, and put a copper wire all around here. Copper wire, put some weights. Now below the copper wire, very high pressure will come, very thin area, more pressure will act. So there you can see ice quickly melt. You keep in a 0 degree room. So no chance of melting it without temperature. During the holidays, so I will give an extra class. Those who want, you can attend. Everything I will go in detail again. Okay.
From the beginning.
Beginning means where we started faster, that area onwards.
Okay, sir.
That means gravitation we finished in detail, right?
No, sir. We got faster.
No, sir.
Gravitation onwards, I will go very slow pace. How much we can finish? Because after that we are free. How much
Yes,
we
sir.
can go in detail, giving slow notes and all, we will go. That's an extra class. Anybody wants, you can come. It's not compulsory because first I'll finish the portion officially. Then I'll go with the numericals and all. So those who can manage yourself with the note and that explanation, okay. Others can attend the class slowly, so no complaints. That's my additional work. Like free tuition I'm giving, those who want, you can attend every day. Daytime, 1 hour daily, I will keep the class. Okay.
Sir, time?
That we'll discuss, it's December. First,
Okay.
let's finish this portion. Afternoon only I'll keep most probably. Because so you all can sleep well and get up in the afternoon and we'll have a little class. That's all.
Okay. Thank you, sir.
What we are doing, sir. We are studying capital. See, this is another problem. This keep joining. This is kept in a container. That container I'm not marking. I'm only showing liquid level here. Actually, it's in a container. This capillary, I told you, microscopic, very small. Then only capillary rise will come. Here I'm showing it little larger. Here, water rising through here. Water rising up to this level, for example. You can also draw the diagram if you want. You can practice it. Yeah. Now, this is a tangent, means surface tension acting here, down, along the surface. So this angle is angle of contact, theta, theta. Now, glass molecule attracted exactly back. That's called reaction. This one here and here. When this forces resultant of this upward force and downward force equal, it will stop there. This is like a hemisphere. Here is the radius r. This is also equal to radius r. Both are same radius, okay? Actually, that should come little one down. Here. Now, this is the, see here. So this height also r. R. Up to here h, because total height why I'm not taking this region, some air is there. See, this region is air, other region only liquid. Then this we are resolving into two components. This one we are resolving into one component here, one component here. Here and here. Okay. So this component, suppose this is R is equal to, this is S. This is S, this is S. Here R is equal to S. So this component is S. This is theta. This is theta, therefore this is theta. So this is S sine theta. This side will be S cos theta. Similarly, S sine theta, S cos theta. This is S. This is theta, this is also theta. This is only 2 points we can show on the diagram. Actually, it is in the circle. Every point around the circle, these forces are acting. Every point. Okay. So S sine theta diametrically opposite, it will cancel. F cos theta will be added up. So in the middle, I'm going to show that. the force acting here is now total, that is 2 pi r. 2 pi r s cos theta is a total one. Now this upward force is equal to the weight acting downward. Weight acting downward. That is mg. Now when these two are equal, it is under equilibrium. This is what we are going to study here. So mg is equal to 2 pi r s cos theta. Okay. mg is equal to pi r squared h. This much portion. Pi r squared h. Liquid volume. Plus this region we need. That is pi r squared into r. Pi r squared into this much region, volume completely r. But from that, this hemisphere you have to subtract. Minus 1 by 3. 2 by 3, right? 2 by 3 of?
1 by 2 pi r, right?
2 by volume, right? 2 by 3 pi r cubed. Isn't it? 2 by 3 pi r. 4 by 3 pi r cubed. Complete. 4 by 3 pi r cubed volume of
yes,
entire sphere. This is hemisphere, so 2 by 3 pi r cubed. Agreed?
Yes, sir.
So this is volume. Volume into density into gravity. Okay? C equal to 2 pi r s cos theta. C equal to 2 pi r s cos theta. So here we can write pi r squared h plus pi r. Here pi r squared we can take commonly out. Okay? So here pi r squared I am taking h plus here it will be this pi r squared I am taking here back. This r minus 2 by 3, this portion, okay? This is separate region, right? Pi r squared plus this region, pi r cubed minus this hemisphere. So that will be 1 by 3, okay? 1 by 3 pi r cubed will come. So that will 1 by 3 r. Agreed?
Yes.
Isn't it? 1 by 3 r here.
Yes, sir.
Pi r squared I have taken outside. Rho g is equal to 2 pi r s cos theta. Here r is very, very smaller. This is very minute radius. So we can write r is very, very smaller than h. R is very, very smaller than h. So h is neglected. R is neglected. Okay. So we can write here pi r squared h rho g is equal to 2 pi r s cos theta. We need h. So now we can cancel. Pi cancel. Here pi cancel. R squared R cancel. Then h is equal to 2s cos theta divided by r rho g. R here r rho g. This will give you capillary height, capillary rise, or if it's mercury, capillary depression. Then minus will come. If it is mercury, it will go down to level. Here it went up. Mercury, if you are taking, it will go down to the level. Now theta for water is 0. That they won't tell you in the numericals. You must know. Theta means angle of contact of water and glass is taken as 0. Just place water on the glass. You can see it spreading. Rho is the density of the liquid. G is gravity. R is the radius of the capillary tube. Okay. S is the surface tension. This is the formula. This derivation is important also. Any doubt? Any doubt?
So, sir,
Can I continue?
Can't we substitute the value of cos 0?
What?
Can't we substitute the value of cos 0?
Cos 0 1.
Yeah. Can't we substitute and
so theta 0. If theta is not given, theta should take a 0 because water and glass is taken as 0, cos 0. Okay, so this is the formula we have. Now look here. Here, same thing I told you. If we are cutting from here, then what will happen to this portion of the water? You don't think it will overflow. That height will adjust. When height is adjusting, what happened to this radius of curvature? That's what you're going to discuss now. Okay, look here. Same diagram, I am going to draw a little different manner now. See, this is the tube. This is a capillary tube. Okay. So here, this liquid meniscus, we can mark, this is a liquid meniscus actually. See here, this meniscus I'm marking here, okay? This portion. This portion. The remaining portion, we are just putting dotted line and making it. When you are drawing it, you can make it a complete line. Okay, so this is actual surface we have under consideration, right? This one. Okay, this one, this portion I'm marking, okay? But if you just extend it, it will form a sphere here, right? Isn't it? So from here, if you're marking, this one here, this is the angle of contact. This angle of contact theta. This is radius. Radius to this, that is R, radius of the tube, R, okay? But radius of this one, curvature, radius of curvature of this one, that is capital R, we can say, okay? Radius of curvature is, this is capital R, okay? Oh, sorry, not there, the upper side we mark here. Here too. Just 1 minute. Let's see that radius, how it's marked. Oh, from angle of contact only that's going. Angle of contact here to this center. Just a minute. This is liquid meniscus. Okay, liquid meniscus here. This is center of this. This we are marking from here to center, this one. And this is radius to this point. This is a radius here. Okay, this is a reference line. There's a reference line connecting here. So this is theta, this also theta. Yeah. This is with the tangent, okay? See here. So this angle, this also theta. And this angle also theta. Okay? This is R, this is capital R. This is center of that sphere. Clear? So here from this diagram, actually this diagram I have drawn from here to this center, this is R, this is H, and this theta and this theta are same. Is it clear?
Yes, sir.
So here if you are taking cos theta in this, cos theta is equal to adjacent side by hypotenuse, R by R. That cos theta will substitute here. Then H is equal to 2S by R rho G. This will be cos theta R by R. Okay. So this R and this R will cancel out. This R and this R will cancel out. Then H is equal to 2S. H is equal to 2S divided by rho GR. This is H. Agreed? So here if I multiplying this R here, H into R is equal to 2S by rho G. Here surface tension of water is constant, density is constant, gravity constant. That means H into R is equal to constant value. So always product of this capillary height, okay? From here to here, that capillary height and this radius of curvature, product will be same. So if you're cutting here, naturally it cannot go to this height. So height will reduce. So what will happen? This curvature, right? This curvature, that will increase. That will go more like this. More flatten up. So that product, so this radius will increase, isn't it? So height and R will be always constant. So in capillary tube, If you're cutting the capillary tube beyond the capillary rise, it will not overflow because adhesion is not there, glass is not there to lift. So capillary rise will decrease. Instead, that meniscus, okay, this surface curvature will go more straighten. That means radius will increase. This has less curvature, right? Less curvature. Now this will have bigger curvature. That means radius of curvature will increase if height is decreasing because h into r remain constant. This is a conclusion over there. Is it clear? And there are many numericals there. You can just check the numericals. Okay. Then I'm going to the next topic, heat. Okay, heat and thermodynamics.
Chapter, right?
Next topic.
Chapter.
Next unit. Unit 10. Heat and thermodynamics.
So, sir, we will again send notes or we will read along with you?
What is that? What do you want?
Sir, you again send the notes of the chapter?
I did not get you.
Will you give notes or we will write now?
Notes, if I'm giving, you must write faster. That's a problem. Otherwise, I'll send until here I gave already note, right? Until capillarize, I gave the note.
Yes, sir.
Yes, sir.
Now this note I will send to you today. This chapter also easy chapter. It's not very difficult. Actually, this is the method in higher classes to teach. But since here we are getting spoon feeding, you are feeling like that. Actually, notes and explanation, if you're giving, you must learn. That's a correct procedure. These notes I'll send to you. Let me finish it first. Then after that, I told you I can go very slow pace. Until your exam, I can go. No problem. Now, heat and thermodynamics. Next chapter. Okay. Actually, we know heat is a form of energy. This note I'll send to you. Heat is a form of energy. It is usually measured as kinetic energy of a liquid or any material. When you're heating, mainly kinetic energy of the molecule only changing. So we can say kinetic energy or total energy possessed by the molecules is a measure of heat of that body. So usually when you're heating, kinetic energy only changing there. So this is the first thing to understand. Okay. Then temperature. Temperature means, it does not mean temperature is heat. Temperature of degree of hotness or degree of coldness. For example, you take 1 bucket of water, say 1 kilogram of water you take, and 1 kilogram of iron you take or steel you take. Both are kept in hot sun. In Saudi and all, very hot in the afternoon. Okay, just keep the noon time, this under sun. Which will be heated fast?
Sun.
Steel,
Right.
isn't it? Steel. But both are receiving same amount of heat, but steel will quickly increase temperature. So temperature is not measure of the heat. Temperature is the degree of hotness. Do you understand? Suppose that it is like this. See, a big vessel and a very small vessel. This has more capacity, this has less capacity. You pour same amount of water. Here water level will be low, here level will be high. The temperature can compare with the level. And heat possessed by it can compare with this water in it. We can compare like that. Do you follow? Is it clear to you?
Yes, sir.
Yes, sir.
So temperature is a measure of heat. Okay. Temperature is usually measured with the thermometer. We know. Mainly there are 4 types of thermometer. First one, Celsius, normal one. Then Fahrenheit. Then Kelvin and Rankine. This Rankine and all now we are not using at all. So basically we are studying now 3. Celsius, Fahrenheit and Kelvin. And we should know the conversion of these 3. Okay. When we are making a thermometer, first we need a long tube, like a capillary in it, almost like a capillary tube. There is a very narrow tube that will be filled with mercury completely. Okay. So this is our thermometer. There are 4 such thermometer we can mark here. No need of 4, 3 enough, because Rankine we are not using now. See here, this is first thermometer. Then here second one. And third thermometer. These are the 3 thermometer we have. Okay. Here, this is full of mercury now. Inside this full of mercury, there is a bulb here like that. Initially, what we do, this thermometer, we keep in a container with ice, pure ice melting at 0 degree. Then we can see that they all will have a mercury in this height. Okay, mercury will be at this point, that particular temperature. This point is known as lower fixed point, lower fixed point. Now on heating, mercury start expanding. So we can say this mercury will keep moving until this point. When it reaching boiling water, water is boiling, this is called upper fixed point. So temperature of the pure melting ice is a lower fixed point. Temperature of the boiling water is upper fixed point. Okay, so this is an upper fixed point. This point here. Okay, this is also upper fixed point. Upper fixed point, upper fixed point. Now, there are 3 thermometers you have. Now, one person approaching you, he want to calibrate it in terms of Celsius. So, first what you do, this lower fixed point, you will mark it as 0 degrees Celsius. Upper fixed point, you will mark it as 100 degrees Celsius. And each division, you will divide 100 divisions in between, 1 division, 1 degree. Now, other person who is approaching Fahrenheit, these people, they are saying water at melting ice, temperature of the melting ice, they are not calling 0 degree. They gave the name 32 degree Fahrenheit. They are telling 0 degree is not the lowest, still it can go down. So they are marking melting point of ice, that is 32, and boiling point of water is 212, and total 180 divisions are there in between. This is what Fahrenheit following. Fahrenheit, F-A-R-N-E-H-E-I-T. Now Kelvin, he is telling lowest point is 273 Kelvin, highest point is 373. In between 100 divisions are there. That means I am giving these 3 thermometers to 3 people. They are keeping these thermometers in ice. If I'm calling him and asking, he will say 0 degree. This person will say 30 degree Fahrenheit. This person will say 273 Kelvin. But we common people are in problem. Because some old people not educated, they may have fever. If you ask them, now most of the people, they know about it. But olden time, this, very people also not educated. If you're asking how much temperature I have, they will say 105 degrees Celsius. Because Celsius is the only thing they know. 105 degrees Celsius, just imagine 100 degrees Celsius, water will boil. 105 degrees Celsius, their blood will be steam, like through the nose and all steam will come out. They will be like steam engine. Is it clear? So this is a wrong notion they had. So you must know correct relation between Celsius, Fahrenheit and Kelvin. For this, we need to develop a formula. That means if I'm keeping this in a particular, all these 3 I'm keeping in a particular boiling water or some heated water or on some body, they all will show different value. This will show T degrees Celsius. This is T degree Fahrenheit. This is T Kelvin. Degree we don't use here, T Kelvin. So all these 3 will have 3 different values. So how a person can understand? 0 degree we know, 32 to 73 we know that. But in between some come, they must know a calculation. For this what we did, we are using Celsius and Fahrenheit, very easy. See, 0 plus 273. Everywhere just 273 if you add, you will get values in Kelvin.
Kelvin.
But Fahrenheit is a problem. Fahrenheit, what we have to do? Here we have to make a graph. Okay, this is T degree Celsius. This is T degree Fahrenheit. And this is 0 degree Celsius, 32 Fahrenheit. This is the way graph increasing. Corresponding to this, this is 212 Fahrenheit. Here 100 degree Celsius. Like this, we make a relation. Increase of temperature will be same in both. Now what we do, here we are dividing this graph into say O, A, B, C, like that. Okay. Now T degree Fahrenheit means someplace we don't know. In between, we are taking a point that's T degree Fahrenheit. Okay. Corresponding value will be T degree Celsius. T degree, this is Celsius scale. Here Fahrenheit scale we are marking. Fahrenheit. Okay. Right. Now A, B, C, D, E, F, G, like that. Now we can take two similar triangles here. Okay. This I am removing from here. If you read the note, you will easily understand it. So not very complicated one, but same day you must read. Look here now. So here A, C, D and A, B, E are similar triangles. So here we can write CD divided by BE is equal to AD divided by AE. AD divided by AE. Okay. What is CD? CD means 212 minus 32. 212 minus 32.
180.
BE
80.
means T degree Fahrenheit minus 32. T degree Fahrenheit minus 32. AD. What is AD? 100 degree. AE is see T degree Celsius. T degree Celsius. Now this is 180 divided by T degree Fahrenheit is minus 32. 100 divided by T degree Celsius. Okay. So this is 29 times 25 times. Then we can write here T degree Celsius is equal to, go this side, 5 by 9 into T degree Fahrenheit minus 32.